class, welcome back again for another lesson. Today's lesson is about alternating current through an inductor. This is class by Raj, teaching for Physics Form 6, Semester 2. Today, the learning outcome will be to derive an expression for the current and to explain the phase difference, to define the reactance and use the formula. Reactance. The symbol of a reactance is always denoted by a capital X. Is a property in an alternating current circuit which oppose the change in the current. Okay. Now, if in the circuit there is an inductor, then the inductive reactance will be given as the symbol of XL. And if in the circuit there is a capacitor, then the capacitive reactance has the symbol of XC. Now, when an alternating current passes through a component, example like inductor and capacitor that contains reactance, then energy is either stored in or released from the magnetic field or an electric field. If it is from the magnetic field, then it must be from the inductor. If it's from the electric field, then it must be from the capacitor. Let's look at the difference between a reactance and a resistance. We know reactance and resistance are opposition. They are opposition, but they are different between both of them is resistance opposed to a flow of current, but reactance is something that opposed to a change in the current in the circuit. In other words, in simpler words, friction against the motion of an electron is resistance. Reactance is inertia against the motion of an electron. The symbol for resistance will be capital R. The symbol for reactance will be capital X. Resistance is found in resistor. Reactance is found in inductor and capacitor. And resistor is found in both AC and DC circuits. And the energy that is prevented from flowing is expelled as heat. That means the energy is dissipated as heat when the current flows in a resistor. But in reactance, because it only affects changing current, reactance is specified only to ACs. And it depends on the frequency of alternating current. Whereas resistance from our previous lesson depends on dimension, which is the area and the length, resistivity and the temperature of conductor. Heat is dissipated, so we can say energy is dissipated, so we can say power gets dissipated. But in reactance, power gets stored. We're going to look at alternating current through an inductor. Okay, so in this diagram, we have a AC supply and it's fixed to a inductor with the inductance L. Okay, so a pure inductor class, what is a pure inductor? A pure inductor has only inductance L. Okay, no resistance and no capacitance. Okay, now let's talk about the voltage here. Okay, the voltage here. So alternating voltage that is applied across a pure inductor of self-inductance L, we say it's V equals to V naught, okay, sine omega t. Okay, so the voltage that is applied across a pure inductor, V equals to V naught sine omega t. Okay, and then if I want to draw the graph will be like this. So it's a sine graph, so the graph is like this. Okay, so if I want to draw here again also, the graph will be, it's a sine graph. Okay, so this is a graph of V, this is a graph of T, and then this one is the peak voltage. V0 is called what? V0 is called as peak voltage. Okay, omega is 2 pi f, angular frequency. Okay, this omega is called as angular frequency, which is 2 pi f. F is frequency. Okay, so that is what we know. Now say for example, what is another concept now we want to find out is the current that flows in the inductor. The current that flows in the inductor. Okay, so the concept is used here is a concept of induction. So I'm going to take a different color pen here. Okay, we're going to look at the current that flows inside the inductor. The concept comes from, we know that to maintain the current in the inductor, to maintain the current in the inductor, okay, the voltage across the inductor provided by the AC, which is V, must be equals to the back EMF, which is negative E. Okay, to maintain the current in the inductor, the voltage provided by the AC supply must be equal to the back EMF, but in opposite direction. That's why you have the negative opposite direction. Okay, opposite direction. So the back EMF, if in this direction, means it will be like this. Okay, E. Okay, and then we know that E is equals to negative L di over dt. Okay, so V is equals to L di over dt. Okay, then we bring here di over dt is equals to B over L, where V is V0 sine omega t. So V0 sine omega t divided by L. Okay, then we take di 1 over L V0 sine omega t dt. Then we integrate. Okay, integration, because this one is a constant, right? So we get I. Okay, so V0 sine omega t, this is 1 over L, yeah, dt. Okay, alright, so I'm going to just write down here. Once we integrate this, we will get negative I equals to negative V0 cos omega t divided by omega L. Okay, once you integrate this, we get negative V0 cos omega t divided by omega L. This one you have to know, you have to memorize how to derive it by the concept. Okay, class, because it is in your learning outcome. Alright, so V0 omega L, V0 omega L is actually is I0. Okay, so I'm going to write it. I0 is V0 omega L. So therefore we get I equals to negative I0 cos omega t. So this will be the graph, this will be the expression for the current. So if I draw the graph will look something like this. So this is the graph for I equals to negative I0 cos omega t. Okay, so the next one, we already know the V, we already know the I, we already derive an expression of the current from the V equals to V0 sine omega t. Now let's look at the phase difference between the current and the voltage for a pure inductor. So point number, this is number 1, this is number 1, this is number 2. Now let's look at number 3. Okay, so if we look at the graph, I want to draw a phasor diagram. Okay, So this one is V naught sine omega t. So the line will be here because it's a sine. The initial is here. So the line or the phasor will be in this direction, which is V. Okay. And then here is the current. Okay. So the phasor will be in this direction, which I've already taught you in the class of under alternating current through a resistor. So here this is anti-clockwise, where omega is in this direction. So when omega is in this direction, the phase difference, okay, the phase difference between V and I is pi over 2 radian. Okay, so we can make 3 conclusion. One thing, the phase difference, okay, the phase difference between V and I is pi over 2 radian. That's the first sentence we can say, number 1. Number 2, what we can say is that we can say, since it's in this direction, right? So V is leading. So we can use the word V is leading, or we can say I lagging behind V. I lagging behind V because it's in this direction, right? It's in this direction. So V is leading. I is lagging. Okay, sorry, I never put I here. I is lagging. This is phasor diagram. Okay, or we can say V is leading. Okay, V leading I. We can also say that V leading I. Okay, so that is number 3. Okay, number 4. Okay, we know already, and we already explained the phase difference between the current and the voltage for a pure inductor. Let's look at number 4, which is reactance. We want to define the reactance of a pure inductor. Okay, so we go back here. Now we're going to look at is reactance. Okay, reactance of an inductor, of a pure inductor. Okay, now we see from here I naught is equals to V naught over omega L, correct? So V naught over I naught is equals to omega L. Therefore, V naught over I naught is called as XL. Symbol is X. X is actually called as what? Is reactance. Okay, X is what? Is reactance, and L is an inductor. Okay, XL, which is the reactance of the inductor, is actually the opposition. Okay, opposition of the inductor to the flow of change of current, to the flow of change of an AC. Okay, opposition of the inductor to the okay, the word to the flow of change of an AC. So XL is equals to V naught over I naught, which is equals to omega L. Okay, so sometimes XL we can also use in respect of RMS. We can also say V naught is what? VRMS times with square root of 2 IRMS times with square root of 2, which is equals to VRMS divided by IRMS. This one reactance in respect to peak. Okay, we are talking in respect to peak. This one reactance in respect to root mean square.
Alright, so here what is important here, okay, let me write down here. Okay, XL is equals to omega L, so XL is equals to 2 pi FL. So XL is directly proportional to frequency. Okay, XL is directly proportional to frequency. So if I draw a graph of reactance of an inductor, which is this is XL and this is frequency, the graph will be a straight line. So we have four important points here, class, just a summary. First, V equals to V naught sine omega t, and then we have to derive the expression for the current from V equals to V naught sine omega t, and then we compare between this V and this I, okay, by using a phasor diagram, and we can get three important information. And then we know the reactance of a pure conductor. Reactance means is X, pure conductor means then we have XL. So reactance is what, class? Reactance is actually is a opposition of the inductor to the flow of a change of an alternating current, and then the formula will be V naught over I naught, or VRMS over IRMS, or we can say is omega L. Okay, so just going to summarize here. What is the reactance of inductor? XL is V naught over I naught, or VRMS over IRMS, or is omega L. Okay, or is omega L. Okay, alright. So, or we want to say omega is 2 pi FL also, because we substitute omega as 2 pi F. Okay, alright, so that is it.
Our next learning outcome is to derive and use the formula for the power in an alternating current circuit which consists of only an inductor.
At power, okay, we're going to derive and use the formula for an alternating current which consists of only a pure inductor, and then we're going to look and study this graph. Okay, so now we know that V is equals to V naught cos omega t. Okay, we choose V equals to V naught cos omega t, and then if you use the derivation which is from the previous lesson, you will get your I equals to I naught sine omega t. So I'm going to take these two expression for voltage and current. So if you see in this diagram, for voltage is cos, so it's cos, so you can see a cos function graph, and then for current is sine, so you can see sine function graph. Okay, and then the one that this one is the power, okay, is representing power. Okay, so here we know P is equals to IV, so I is equals to I naught sine omega t times with V naught cos omega t. So if I times this and I use my trigo, I should get my solution as half I naught V naught sine 2 omega t. Okay, alright, so here half I naught V naught, half I naught V naught is called as peak power, which is P naught sine 2 omega t power. Okay, so what is peak power? Peak power is equals to half I naught V naught. Okay, so if I draw, it looks like the power is in the function of sine. So if I draw, you can see in this diagram which is the power which is in the sine function. Okay, the graph is in the sine function, where the peak power is half I naught V naught. Okay, Alright, so now we're going to look at the graph. Now, if you see this graph, okay, before we look at the graph, let's draw a diagram. A diagram of a AC. This is an inductor, which is inductance L. Then we have a AC, right, V. Okay, alright. Now, in this diagram, if you see, there is two signs of power, which you can see here is a positive power and here is a negative power. Okay, now positive power, okay, I'm going to write down here. Positive power means power is provided by the AC. Power provided by the AC. Okay, by the AC. Negative power means power returned by the inductor. Power returned by the inductor to the AC. Okay, I'm going to write there, to the AC. Power provided by the AC to the inductor. So let me finish that sentence completely. Okay, so if you see in this diagram, positive power means power provided by the AC to the inductor. Negative power means power from the inductor returned back to the AC. So this will be negative power. Okay, another two important thing about this graph is that, okay, area under the graph, the blue line here, is energy. Okay, energy supplied, okay, to inductor by AC supply. Okay, alright. And then area under the graph in the power negative, the area under this darker blue graph, represent energy returned by inductor to AC supply. So these are the important things that we can use to describe the graph. Okay, let's describe the graph, which we are going to look at two time. Okay, so here we have from 0 to t over 4. Okay, 0 to t over 4. So time 0 to t over 4. Okay, what can we say? 0 to t over 4, we realize that power is positive. Okay, power is positive. We know power positive means power returned by the power provided by the AC to the inductor. Okay, so power is positive. Then we can say, next keyword we can say is energy is supplied. Okay, energy is supplied to inductor by AC. Energy is supplied to inductor by AC supply. Okay, alright, the next keyword is, we can say, okay, that energy stored in the inductor is maximum at, okay, energy stored in the inductor is maximum. So energy stored in the inductor is maximum at this particular point, and it happens at t is t over 4, it happens at time is t over 4, and at current maximum, or at when, okay, at t over 4 when current is at its peak or at its maximum. Okay, so energy stored in the inductor is maximum at t over 4 when current is at its peak. Okay, so the first, from 0 to t over 4, and power is positive, power is supplied to the inductor, energy is supplied to the inductor, the energy is maximum and is stored inside the inductor in the form of magnetic field. Correct or not? So that you all know, right? Because energy is stored in the magnetic field. In the magnetic field. That means the strength of the field becomes stronger. Okay? Alright. Then we look at the next one. We look at the next one, which is what? Which is t over 4 t over 2. Okay, t over 4 to t over 2. So we're going to look at this. I'm going to just take another color pen. Okay, so I'm going to take this one to this line. Okay, so what do you see, class? So you see this part of the area. So you can say power is negative, energy returned by inductor to AC supply. Okay, alright, so you can see that, yeah, for these two expression, and these are repeated process. This process is repeated. Okay, so what else can we get from this information is, right, which I'm going to write down in this green color. Okay, now peak power is half I naught V naught. That means peak power. So here will be half I naught V naught. Okay, which will be negative. So 100% energy is supplied. 100% energy is supplied to the inductor, or 100% of power is supplied from the AC to the inductor. 100% is returned from the inductor to the AC. So that means there is no energy dissipated. No energy is dissipated. Okay, so no energy is dissipated. So you see the maximum peak power is plus half I naught V naught. Then this one is negative half I naught V naught. So we can say, okay, I'm going to write down here, yeah. Mean power is 0. Mean power is what? Mean power is 0 for an inductor, because half I naught V naught plus minus half I naught V naught, you get 0. So mean power is 0. Okay, alright, so that is the most important concept. Okay, what you have to know is you have to derive and use the formula. The formula is based on what voltage or current, what voltage is given, because from the voltage you can know how to derive the current. And then you have to know about peak power, mean power, okay, and then you have to learn about the power, what is positive power, what is negative power, then energy supplied, and then energy returned, and then you have to know how to describe this part of the graph. Okay, so that is all, class. Thank you.